we're good to go. Okay, yesterday, actually, I think this class, I think we actually talked about this, right? But whatever. We did. Oh, we did A and.
No.
Okay, we did 5 together, and then I said go do A and B. Okay, all right. So for the sake of, I don't think I got to quite the same place in the other 2 classes, so we'll just kind of recap. To solve something like this, we have a square root. To get rid of a square root, you do the opposite thing, which is squaring. So if we square both sides, the square root of x times itself, or squared, what happens is that we just lose the square root. And 3 squared is 9, and that's it, right? So how does that affect or change, if it does at all, what we would do here? Okay, maybe we could. Okay, let's think about where we're going to go eventually. Because there's a square root, I'm going to end up squaring both sides, right? When you square both sides, the both sides part is important, right? Anytime you do algebra stuff to move things around, you do something to one side, you have to do the same thing to the other side, otherwise you change things, right? So I'm going to square both sides, but we have to square the side as a whole. So if I try to do that as it is right now, that means squaring that. And squaring means take 2 copies of it and multiply them together. And if you multiply 2 copies of that thing together, it's, basically a binomial. Treat this like it's one piece. But then you've got these 2 terms that you're multiplying, and there it's fine. But then look at what happens with the outer and inner parts of the product. And then minus 3 times minus 3 would be plus 9. What was the point of squaring? Because I wanted to get rid of the square root, right? When I squared this thing as it is right now, did I accomplish that? And I mean, I would say that we made things worse, right? Okay, so how should we change what we've done so far? Yeah, put the 3 back, right? Never mind 3, you go back over there, right? Because we're squaring the side as a whole, I want to square just the square root term, right? Because I don't get to like pick and choose where things get squared. You don't distribute exponents. That part's important. Exponents or powers. Don't distribute. Right? Think about order of operations. Powers happens, or exponents happen before other things. Things are grouped, happen before powers do. So you can't distribute an exponent across a grouped thing, which is why the thing I had here a minute ago ended up being as messy as it was. So before I square, I want to get the thing I'm trying to square, like the reason I'm squaring, I want to get that thing isolated first. Now here that's already done. So we can square both sides. On the left-hand side, we're squaring a square root. So what happens? We just get rid of the square root. We get x minus 2. On the right-hand side, we're squaring 3, which is 9. And then, well, finish whatever's left to be finished. Add 2 to both sides. So x is 11. What would that mean for b then? First thing I should do is move 1 to the other side so that I can square, and then, of course, it's turned into the same problem, but so that I can square, so that I can get rid of the square root and then continue on and solve. So if there's a single radical term like this, We want to isolate or solve for it first. Then get rid of it. And that's pretty much in line with a lot of other stuff we've done up to this point. If there's one, sort of term or piece of the equation that I know I'm going to have to sort of think about and deal with, if we can just move stuff around to get it isolated, to get it by itself on one side of the equation, is generally a good idea to do that, right? The exceptions, the times that we don't do that, is when we can't because there's more than one term, right? Like a quadratic. There's an x squared term and an x term. I can't move stuff around to get, both of those things by themselves at the same time, right? So we, go to other stuff. But if we've got like a single absolute value term or a perfect square or a square root or, just one rational term, a lot of those we had more than one, so we couldn't do it again there. If we have just one, generally the idea is get it by itself and then think about how you break it down or get rid of it. Okay? And the way you're going to get rid of things is pretty much what we did here. The reason I squared here is because this was a square root. And squaring is the inverse or the opposite operation to taking a square root. So how would things change if this had been a cube root? Then instead of squaring both sides, I would cube both sides. And the only thing that would change, left-hand side would again just be x minus 2, right? They would undo each other. But on the right, I would get 3 cubed instead of squared, which is 27. And, then again, I just finish from there, right? Okay. Talk to me about what we can do here then. So first thing is, similar, we talked about this with the domain thing yesterday, right? Number one is think about what kind of thing we're dealing with. Here, I look at this, the part that makes me maybe the most nervous is this thing, right? Okay, well, I've got a square root in there, so I know I'm going to have to square to get rid of it. And I know that to square and get rid of it, I probably want this thing to be alone on one side of the equation if I can, make that happen, right? If I can get it to that point, that's what I'm looking for. Now here, that's already done for us, right? It's the only thing on that side of the equation. So we're good to go to sort of jump into it. But if there was other stuff on the left-hand side with that, I would want to like move that over, right? Okay, so what do we do to get rid of the square root then? Square. And when we square a square root, we just get the stuff inside. But if I square one side, I got to square the other. So on the other side of the equation, I get x squared. So we took this equation that had a square root initially, we squared both sides to get rid of it, and now what do we have? A quadratic. Oh, man. Good thing we know how to solve quadratics, right? Whew, man. Look how many times we'd be up a creek if we didn't. All right, so it's quadratic. We need to solve it. What do we do? Get it all to one side. Okay. I'm going to move stuff over here. It doesn't matter. You can move either way. X squared plus 5x minus 6 equals 0. It's quadratic. We know a little more enthusiasm. I know it's early yet, but so we can solve it. This one does factor. What multiplies to negative 6 and adds to 5? Okay, so x minus 1 is 0, or x plus 6 is 0. Okay, check your, like, multiply back out and see what you get. 5 and 6 as B and C, like any combination of the signs here, they all factor, but they all factor differently. So just, check yours.
This reminds me, Dr. Thomas.
Uh-huh.
What was the answer on formulas on a test like the last one?
Oh, I need to.
Sweet, thank you.
Uh-huh. Written on the palm of my hand now, which is pretty much foolproof way to remember things. So, what's that?
Yeah, I did it wrong, but I don't know.
Okay. Give it another shot. Let me know if I need to tag in. But so we get 1 and negative 6. That's fine too. You don't. You never have to factor things. Or the only times that you sort of need to give something in factored form is if you have like a graph or something, you can get it a different way, right? You never strictly have to do this kind of factoring. Okay. But there's a little bit of a catch. Because the thing that we started with was the square root, right? And square roots, let's actually just graph it. Square roots look like that. And this one in particular was what, 6 minus 5x? Okay, so there's like a shift and a stretching thing and the reflection. This one looks like that. And it's got restrictions on its domain and its range, right? It's not defined everywhere. But what we did was take it and square both sides. And when we squared both sides, it turned into a quadratic, right? And quadratics don't have any restrictions on their domain, right? They're defined everywhere. And their range is sort of half infinite thing, but their domain is all real numbers. So we took this thing that has this sort of restricted information about its domain and range. It doesn't exist everywhere. And we transformed it into an equivalent thing that doesn't have that same kind of, like baggage about its domain. If I throw y equals x on there, when we solve this equation, we're talking about where they intersect. And what do you see as far as where they intersect? At 1, 1. Uh-oh. There's only one of them. How many did we find? 2. What does that mean? One of them's not really there, right? One of them's extraneous. It's like a false positive kind of thing. So let's see where and why that happens. If I take x equals 1 and plug it into the original equation, and now I'm thinking about it like a question, right? Is the square root of 6 minus 5, and that's 5 times 1, right? Because I plugged in x equals 1. 5 times 1 is 5, 6 minus 5 is 1. Is the square root of 1 equal to 1? Yes. Okay. That's definitely an actual solution then, right? That actually works. If I try negative 6, though, 6 minus 5 times negative 6, that's the square root of 36. But is the square root of 36 negative 6? No. Right, grab your calculator, type in the square root of 36. It tells you that it's 6. Because the square root as a function, as an operation, as a button on a calculator, is defined to be the principal or the positive one, right? Now, if you square negative 6, you do get 36, but that doesn't mean the same thing as saying that the square root of 36 is negative 6. That's our extraneous solution. That doesn't work. X equals 1 is the actual solution to the equation. Okay? What we're seeing is sort of an artifact of, think way back to when we talked about inverse functions, right? To have an inverse, a function needs to be 1 to 1. It passes a horizontal line test, right? Does a quadratic like x squared pass a horizontal line test? No. What that means is that if we flip it over on its side, we get a thing that's not a function. So the way we deal with that is to throw half of it away and define the square root function to just be pew, right? The positive half, right? The top part of the thing. What we're doing here when we squared both sides and got this equivalent but not quite thing to solve that's easier to work with is we said, okay, I got this square root, but square roots are kind of scary and intimidating, and I'm not sure how to do this. So let me turn it into a thing that I know how to deal with. But when we do that, sort of baked into the background of the algebra stuff that we're doing, is when we do that and take this square root and turn it back into a square, we're replacing the half that we deleted before, right? And that's where this would show up. If I filled in the lower branch of this sideways parabola, it'd be right there and it would hit this line at -6. Only that's not really part of the actual function that we started with. So what we have to check for is that solutions that we get here, and this is going to be particularly important when it's something where we take a square root and we end up with like a quadratic or something where there's more going on, right? It's not really an issue here because I'm just squaring a number. That's a well-defined thing. But here, because I'm dealing with squares and squares have this domain and range, stuff about them that we've talked about yesterday. Once I get to solutions here, I have to make sure that those still make sense in the original context, right? And the way you do that is just to sort of plug them in and see if they work or not. And it should be something kind of as like apparent as that.
I have a question.
Yep.
So whenever you do square root of 1 equals 1.
Yep.
You would just find the square root and make sure it's 1.
Yeah.
Okay.
Yeah. Make sure it's the same thing. The square root of 1 is 1. The square root of 36 is not a negative though because that's not how square roots work. Okay. I'll give D a shot. So when it's something like this, where it's just numeric stuff, the same thing will happen, right? It's when you've got some kind of variable that you end up sort of manipulating as well. Yep.
I wouldn't really ask, but I can't find it right now. Okay, remind me.
Yeah.
And then square root of
B squared
minus B squared minus 4 AC over 2.
Yep. Okay, so I see a square root. To get rid of the square root, I'm going to need to square. To really get rid of the square root, I'm going to need to square just the square root, right? So what do we do first?
Get that extra big.
Yep, move that x to the other side. Check. Okay, then what? Square it. If I square that, square root goes away. I just get 11 minus x. That's good, right? That's moving in the direction of making my life easier. But we got to square both sides. So I don't get to, just get rid of the square root for free, right? So on the left-hand side, my life's getting easier. On the right-hand side, things are getting a little bit more complicated, but in a way that we're sort of better equipped to deal with, right? Right-hand side is 1 plus x squared, which is 1 plus 2x plus x squared. All right, squaring a binomial means multiply it by itself. You multiply it by itself, you expand everything, you get that. Okay. Which is, big surprise, right? Quadratic. So collect everything to one side. Two x plus another one. 1 minus 11. Well, now they're not aligned with. Sorry, I'm going into crazy people mode here for a second here. All right. I just had to line everything up. Okay. X squared plus 3x minus 10. Quadratic. Solve a quadratic, right? It's equal to 0. Solve that. What do you get? So -5 and 2. Everybody agree? Okay. -5 and 2. Okay. However you go about solving the quadratic. It does factor. Quadratic formula if you don't want to. It does factor. We get -5 and 2. Okay, so we've solved, but again, anytime anytime we start with something that has, weird domain issues, right? Basically, that's the kind of guideline for when you need to check, right? If you start with a thing that's got where the question, hey, find the domain of this, would mean you have to do something, right? You don't just already know it. Then probably if you solve an equation, you want to go check and see if those still work in the original problem. So that would be rational functions, right? Things with x in the denominator. Square roots, right? That's pretty much all we've got at this point. If I was doing this with a cube root, though, I'm not as concerned because cube roots don't have weird domain stuff, right? They don't behave quite the same way. That means they don't introduce some of the same problems. Okay, so I'm going to check those. I'm going to check them by just rewriting the original problem and plugging in these x values. So is the square root of 16 plus 5 equal to 1? No. So -5 is an extraneous solution. And I feel pretty good then about where 2 is going to go because, it's just sort of how these things work. But probably we want to go ahead and check. That's the square root of 9 minus 2. 3 minus 2 is 1. So x equals 2 is the solution to this equation. Okay. Questions about stuff so far? You can check by the graph. Yeah. As long as you know what you're looking for. Yeah, you can do it that way. If you're going to do that, maybe just draw me a little graph or something. Again, the checking thing, right? Even when they work, do something to show me that you've thought about it, right? So that could be sketching the graph because, again, you've got calculators. You can look at it that way. You can do it sort of numerically like this. Okay. A little bit of a difference though is that for this kind of equation where I've got a square root of something and I end up squaring both sides and ending up with a quadratic, there's a difference in what's going on sort of underneath here than when we solve the rational functions, right? Rational functions, it's that, okay, sometimes we happen to land on a vertical asymptote or whatever. Here, it's kind of more like fundamental almost that if I end up with 2 solutions here, one of them is almost certainly going to be bad. Like it doesn't have to be, it's not that you always throw one of them out, but it's much more likely because it's, again, this idea of, the square root being like half of this sideways parabola. And when we're solving, we're kind of restoring the other half, right? So it's much more likely that we get, like one of the 2 not working, if that makes sense. Again, doesn't mean it has to. You can get 2 solutions and they both work, but it's more likely. Okay, well, flip over to, we'll get these on the back. They look a little different, but are they actually? I mean, yes and no, right? What is that? That's a cube root squared, right? Okay, so it's written with a power instead of being written with a radical, but it's a power that means a radical, right? So 2/3 power means a square and a cube root. Oh, hang on. One of my esteemed colleagues shared I don't know where it is. Never mind. I'll try to find it for next time. But a very charming drawing. So how would you rewrite this then? Okay, we can definitely move the 3 over, and that's a good place to start, right? Just get it out of the way. X minus 4 to the 2/3 is 16 then, right? It never hurts to isolate the quote messy part if we can, and generally it's if not essential then important. Okay, so that helps, but we still have to at some point deal with what this 2/3 power means.
The square root with the 3 in front.
Okay.
X minus 4 squared.
Yep. Okay. Now take a minute and think about where you would go from there. To get x by itself, we're going to need to do three things at some point, right? We're going to need to get rid of the square, we're going to need to get rid of the root, and we're going to need to add 4. Now, adding 4, that's kind of, buried in the furthest, so that's going to be the last thing we do. But the other two, we can peel away in either order, right? Now, the way I've written this, the square is the outermost thing, but again, that rational exponent, you can rewrite those in either order. So you can put the square underneath the radical if you wanted to. But we're going to need to get rid of both of those things. Well, how do you get rid of the square? Take a square root. Yeah, do the opposite. If I take the square root on the left-hand side, it's the square root of a perfect square. Those undo each other, and we're left with the stuff that was inside the square, which is just this cube root. On the right-hand side, we get the square root of 16, which is 4. But since we're the ones who decided to take the square root, we also pick up plus or minus. Right? Think about it this way. If something squared is 16, what could the thing be? Well, either 4 or negative 4. Right? Squaring either of those would give you 16. Okay. Then what? Cube both sides. On the left-hand side, those are inverse operations, so they cancel. On the right-hand side, 4 cubed is 64. So positive 4 cubed is positive 64. Negative 4 cubed is negative 64. Now at this point, and like you may want to do this even, a step before or something when you see that plus or minus show up. But that really means there are two things here, right? One of them is x minus 4 equals 64. The other one is x minus 4 equals negative 64. Last thing to do to solve would be to move the 4 over, right? So add 4 to both sides. X is 68 or negative 60. Okay, so let's just kind of walk back through things first. We moved the 3 over, right? It was times 3, but the 3 is not part of the exponent, right? The exponent's on the x minus 4 term, not a little thing. So divide the 3 out of both sides to get rid of it. At the very least, that makes life easier. 2/3 power means a square and a cube root, right? Now, I would, write that out because it helps us kind of see things. You don't strictly have to. If you notice what we did, we took a square root of a cube. Another way that you could, write that or express taking a square root and cubing would be raising both sides to the 3/2 power. Right? If I did it kind of all at once, 2/3 power times 3/2 power is 1, right? So those cancel over here, and then you figure out what 16 to the 3/2 is, which you can just do directly in a calculator. It's 64. The reason I don't like this as much, this half power still means a square root, which means you still pick up a plus or minus, but when you write it like this, it becomes a lot more difficult to sort of keep in mind that what you're really doing is a square root, and that really means that this comes along, and so you tend to drop the plus or minus, and I mean, like, even I would probably do that sometimes. So that's why I don't usually write it this way. I just kind of think about it as doing like, sort of 2 steps to do the same thing. But, you do you, whatever you're more comfortable with. So we get that. We took a square root of 16, then we cubed it, we get 64. Again, because we decided to take a square root, we get a plus or minus. That would happen with square roots, 4th roots, 6th roots, but not odd ones, right? Odd ones don't do the same thing. And then solve these two things. Now, is this a place where we strictly speaking, would need to check that those work in the original problem? I mean, we certainly can, right? Like you can always plug back in and check and make sure things work. Is this a place where we need to be worried about it? What's different about this than the one before it or the couple before it? It's a cube root, right? And cube roots look something like that. They don't have the same domain issues, baggage, whatever you want to call it, as square roots, right? A square root, we take a parabola, we flip it over on its side, but to make it a function, we have to throw half of it away. Cube root, we just take a cubic and flip it over on its side. We don't have to do the thing where we get rid of half of it. So because of that, I don't need to be as worried about whether those work in the original problem or not. If this had been, some kind of even root, like if this had been a square root or a fourth root or something instead of a cube root, then I would be a little more concerned about it. Again, you can always check. So if you want to go with the, make sure your bases are covered version of things, then, plug it back into the original thing real quick and make sure they work. But we don't need to be as concerned about it for an odd root. Okay? Okay. All right. F is going to be very similar then, right? 3/5 power. Again, move stuff around to get this thing by itself first, and then, think about sort of peeling those away one at a time. You do this one. Okay. One other sort of kind of equation to look at. Look at G and F. G and H, sorry. What do you see? Say again. Okay. That's generally a good thing. What else? There's two of them, right? And there's two of them. Carly doesn't like that. I feel you. There's two of them. If there's two of them, that means we can't get one by itself without the other one, sort of gumming things up somewhere, right? The other thing that you jump out as again is these rational exponents, right? I've got a power of 2/3 and a power of 1/3. Let's start with maybe thinking about how we could rewrite those. A 2/3 power means, I guess we just did a 2/3 power, right? It's a square and a cube root. So the cube root of x squared. And a 1/3 power means cube root. Okay, now this is 5 times x to the 1/3. The power is only on this part, right? So it's 5 times the cube root of x. I'm just going to throw a set of parentheses around that to kind of separate it a little bit. So we're for sure, we know that the 5 is not under the radical or part of the index or whatever. Okay. So this thing is really this other thing then, right? Written in terms of the cube root. Okay. Since there's two of them, again, we can't really just move stuff around to get the messy part by itself to start getting rid of it, because if I move stuff around, then both sides are going to get messy, right? So I can't just go at it that way, which means I have to look for some other way that I can proceed here. Now that we've rewritten it, do you see anything else we might be able to use? Okay. This one's squared. This one's to the first. So they're not like terms, so we can't just add them together, right? Well, they're not, we could multiply them, only we're not multiplying, right? We're adding.
Can we cube it? Because it's going to be quadratic if we do that. Cube the entire thing, including the 6. And I guess the 5.
The problem with that is that if you do it to the entire thing, you have to do it to the entire thing like that. So you would have to distribute. Okay. Things aren't going to clean up as nicely as we would want them to. Hey, those two things are the same, right? What if we just pretend that's not there for a second? There. Now we can really pretend it's not there. It's quadratic. It's quadratic in terms of, well, whatever that pink thing is, right? Okay. It's quadratic with, A being 1 and B being 5 and C being 6. Can we find things that multiply to 6 and add to 5? Sure. 2 and 3 would work, right? Or we can use quadratic formula or whatever, right? The difference would be that it's not x plus 2 and x plus 3, it's pink blobby thing plus 2. It's one of my favorite things I get to do. So like I don't care if you don't like me doing the pink blobby thing or not. I'm going to keep doing it. They're the same, so we can pretend that the scary part's not there, right? And we can factor the thing just like it's any other quadratic because they're the same. Now expand this, right? Get this times this is the thing squared. Plus 2 of them, plus 3 of them, 2 and 3 is 5. And then plus 6 for the last term. So that does factor like that. And if it factors like that, then as usual, we can use the zero product property to split things up and say, okay, well, either this thing is 0 or this thing is 3, or sorry, either this thing is 0 or this other thing is 0. There we go. Said it wrong. Which means that could be -2 or -3, right? If I move the plus 2 and the plus 3 to the other side of the equation. So if whatever this pink blobby thing is -3, then this would be 0, which would make this 0, which would make the original thing 0, right? That's what we're saying. And at no point has it really mattered that it was the cube root of x anywhere, except that these were the same thing, right? That these were both the cube root. Okay, well then we get to do the fun part, and only it's probably not going to work because I end up screwing this up every time. But really, all along, it's like I don't know, people still understand Scooby-Doo references. It's like an episode of Scooby-Doo, right? Like all along, it was Mr. Withers who owns the haunted amusement park, right? Trying to get those meddling kids. All along, it was the cube root of x. So there's one last thing to do. If the cube root of x is -2, what's x? How do we get rid of the cube root? So x would be -8. Or -27. And then again, since we're dealing with cube roots, I don't need to be as concerned about, solutions working in the original problem or not, or getting like false positives and extraneous solutions and that kind of thing. Of course, you can check them, but these will work. Okay, so again, sort of leveraging this quadratic form or quadratic structure to the thing, treating it like it's a quadratic, ignoring the scary part until we can't anymore, right? And then by the time we sort of use the structure of the thing to break everything up, we're left with something that's, not nearly as scary as what it would have been originally. Right? Okay, the one next to it, of course, should feel pretty similar, so work through that one. There are 2 inequalities there as well. The way you do inequalities here is the same way you always do inequalities. They're equations that we've solved already. So just try to do the inequality thing to, figure out what intervals satisfy this. And we'll talk about that first thing Thursday, and then just kind of start reviewing and prepping for things. Okay? Have a good day. I'll see you all on Thursday.